Hello and welcome. Thank you for joining me. My name is Alon Sela, and today we're going to continue talking about the Langevin stochastic differential equation. Let's recap about what we've done so far. We said that this is the Langevin equation where m is the mass, gamma is the friction coefficient, and eta at time t is a Gaussian white noise with these properties. We said that the expectation of eta at time t is equal to 0, and this thing right here, which is called the autocorrelation function, is equal to some constant gamma times the Dirac delta function. I also mentioned that even though you might not know what exactly is a Gaussian white noise, you don't have to know it in order to continue doing this calculation with me. The only important thing to note is that the expectation of this expression is 0, and the expectation for this expression is gamma times the Dirac delta function. We also saw that the expectation of the velocity at time t is equal to some initial velocity v0 times e to the minus gamma t. And today we are going to continue by finding the second moment. So basically we want, we want to find the variance for the velocity. We want to find the variance for v at time t. This is what we want to find, and this is equal to the second moment, v squared t, the second moment minus the squared of the expectation of v at time t. So this thing right here we already found. Okay, and we are going to focus now on this expression right here. After we'll find it, we will be able to calculate the var for the velocity. So let's see. First, we also saw that the solution to the velocity at time t is given by this expression right here. So first of all, if we want the second moment, we need to find what is v squared. So basically we need to square this quantity, and which is equal to this squared. Now I'm going to use the very simple formula a plus b squared, which is equal to a squared plus 2ab plus b squared. So the first expression, this will be a, let's choose another color. This thing right here is the a, and this entire thing is b. So we need a squared, so let's write it. This is equal to the first term squared, so we have v0 squared times e to the minus 2 gamma t plus 2 times the first expression e to the minus gamma t times the second expression times 1 over m times the integral from 0 to t e to the minus gamma t minus t prime eta at t prime dt prime, and plus the second term, the b term, squared. So if I am going to square this thing right here, this is going to get squared, and this is going to get squared. So we're left with 1 over m squared times the squared of this integral, 0 to t e to the minus gamma t minus t prime, eta at t prime dt prime, the whole thing squared. So this is our expression. So now let's see what we can do next. So let's take the expectation, because basically we want to calculate the second moment, which involved taking the expectation of this quantity. So we want this thing right here, and note that if I'll take the expectation for this expression, the expectation is a linear operator, meaning that I can take the expectation for this plus the expectation for this plus the expectation for this. Now this thing right here is a constant. V naught is some initial velocity, e to the minus 2 gamma t is a constant, and therefore when I'll take the expectation for this thing right here, it will be the expression itself. So V naught squared e to the minus 2 gamma t. Same for this thing right here. When I take the expectation for the second term here, 2 times V naught times e minus gamma t times 1 over m is a constant, and we can pull it out of the expectation. So plus 2 V naught e to the minus gamma t times 1 over m times the expectation for this. But as we said in the previous lessons, the only thing that is random here is due to the Gaussian white noise, so we can pull the expectation inside. So when I'm doing it, I will get 0 to t e to the minus gamma t minus t prime, the expectation of eta at t prime d t prime, I'm sorry, d t prime, not squared, and plus this thing right here. So again, this thing is the expectation for this expression. This 1 over m squared is a constant, so we can pull it out of the expectation. And now be careful, we need to take the expectation for the squared integral. So we have the squared 0 to t e to the minus gamma t minus t prime times eta at t prime dt prime squared the expectation. Okay, so let's see how we can simplify it a little bit more. So note that by the definition for the Gaussian white noise right here, eta at any time, the expectation of eta at any time is 0. So instead of t, we can just replace it with t prime if it's if you are getting confused by it. So this thing right here is equal to 0, and therefore this entire product is 0, the entire integral is 0, and this entire expression is 0. So this thing is 0, and we are left with V naught squared e to the minus 2 gamma t plus 1 over m squared times this thing right here. And let's see how we can so let's write it just one more time. The expectation of you know what, let's just do it. So we got the integral squared, so let's write the integral squared. So we have integral from 0 to t of e to the minus gamma t minus t prime eta at t prime dt prime times itself, so 0 to t e to the minus gamma t minus t prime times eta at t prime dt prime, and this entire thing is inside the expectation. So the next thing that I want to do, first of all, let's make a little bit of room. Okay, so basically the thing that we can do next is note that we have this product of the integrals, and I can do something like this. If I have an integral 0 to t of x dx, it is equal to the integral from 0 to t y 0 to t, sorry, y dy. This is the same, we get the same value here. Okay, it doesn't matter if you use x dx or if we use y dy. So let's apply the same reason, the same thinking. Let's apply it here. Instead of t prime, let's replace it with t1. Here we also, instead of t prime, let's replace it with t1. And here, instead of t prime, we can replace it with, let's say, t2. And here we will replace it with t2. And here we're going to replace it with t2. And of course, here also I should have replaced it with t1. So the reason we've done this step is because now we can, first of all, mathematically it's okay to do it. And the second thing is that we are now going to pull the second integral inside the first integral. So let's see what we are left with. We have, you know what, let's deal with this thing right here. Let's call this expression I. So basically we are left with v naught squared e to the minus 2 gamma t plus 1 over m squared times 1 or I, it doesn't matter how you want to call it. So let's find expression for I. So we have the expectation for 0, the integral from 0 to t e to the minus gamma t minus t prime eta at, I'm sorry, not prime, we change it to 1, t1 eta at t1 dt1 times the integral from 0 to t e to the minus gamma t minus t2 eta of t2 dt2, the expectation for this expression. Okay, so let's see, now we can play with these two integrals, and the next thing that we can do, let's say that let's put this integral inside this integral. So we'll have that the first integral or the second integral is 0 to t of we have e to the minus gamma t minus t2, we have eta at t2, and we pull this entire thing here inside the second integral. So we'll also have the integral from 0 to t e to the minus gamma t minus t1 eta of t1 dt1. Okay, and then we'll close it with the dt2. So this is the phrase for the first integral, and we place it inside the second integral. And of course we need to add the symbol for the expectation. So now note that the first integral is with respect to t1. So eta at t2 has no t1 in it, and we can pull it inside the first the first integral here. So which is basically now the inner integral. Let's say it's more right to pronounce it like it. So let's see what we have. We have the expectation from 0 to t of e to the minus gamma t minus t2, and now we are pulling this inside. So we have the integral from 0 to t of e to the minus gamma t minus t1, and we have eta at t1. We are pulling this inside, so we have times eta at t2, we have d t1, and we have d t2 and the expectation. So let's see, this is the inner integral. Okay, now the reason we've done all this is to get to this point where, note that the entire as we said before, the entire randomness is due to this thing right here, is due to the Gaussian white noise. So this thing and this thing, they are constants, so we can take it, not constant, but they are not they have no randomness in them. The randomness is due to this thing right here, so we can take the expectation and put it only on the random thing itself. So we'll get the integral from 0 to t of e to the minus gamma t minus t2 times the integral from 0 to t of e to the minus gamma t minus t1 of the expectation of eta at t1 times eta at t2 d t1, I'm sorry, the expectation, let's close the symbol for the expectation, and d t1 and d t2. And now look at what we've got. We've got the expectation for this product, but this is exactly the autocorrelation function. Let's see, this is exactly the autocorrelation function for the Gaussian white noise. Note that instead of t we have t1, so instead of t we can put t1, and instead of t prime we have t2, so we can put here t2. So this autocorrelation function is equal to gamma times the Dirac delta function. So this becomes the integral from 0 to t e to the minus gamma t minus t2 of the integral from 0 to t of e to the minus gamma t minus t1 times this thing right here is gamma times the Dirac delta function of t1 minus t2 times I run out of place here, d1, and close it with d2. Okay, now let's see. We said that this gamma is a constant, so we can pull it out of the entire double integral. So we are left with, we have gamma times the integral from 0 to t e to the minus gamma t minus t2 of the integral from 0 to t e to the minus gamma t minus t1 times the Dirac delta function t1 minus t2 dt1 dt2. And now it is important to note that we have some function inside the inner integral. We have some function times the Dirac delta function, and according to the properties of a Dirac delta function, when we are multiplying some function times the Dirac delta function and take the integral, what we are left with, let's just put it here on the side so it will be clear. So when we have integral from we say from minus infinity to plus infinity of some function of x times the Dirac delta function of x minus x naught dx, this thing right here is equal to f at this x naught. I'm not going to explain why this is true, because this is basically out of our scope right now, but I'll make another video which explain about the Dirac delta function and its properties. But for now you can take it as granted and apply it. Let's apply it here. So basically what it says that we have let's see, so we have gamma, I'm sorry, gamma not f, gamma times the integral from 0 to t of e to the minus gamma t minus t2. Now this entire integral here, we are saying that this is equal to e to the minus, this is our function that we are multiplying it by the Dirac delta function, so it should be equal to the function itself, e to the minus gamma t minus our variable here is t1. This is integral with respect to t1, so we need to replace instead of the variable, we need to replace this number right here. So instead of the variable, we need to replace it by t2, and so this is the value for the inner integral, and we have dt2. So this is what we have, and now this is become much more simpler. We have the integral gamma times the integral from 0 to t of, we have here e to the minus 2 gamma t minus t2 dt2. Okay, so this integral right here, let's solve it. So we have gamma, this is integral with respect to t2, so we'll have times e to the minus 2 gamma t minus t2 divided by, we have minus 2 gamma times minus, let's write it here because I'm confusing also. So we have minus 2 gamma t, minus and minus is plus, plus 2 gamma t2, so the derivative of this with respect to t2 is just 2 gamma, so divided by 2 gamma, and lower bound is where t2 is equal to 0, and upper bound is where t2 is equal to t. So we'll get, we have gamma over big gamma divided by 2 little gamma times, let's see, we have e to the minus 2 gamma t minus, instead of t2 we are plugging t, and minus e to the minus 2 gamma t minus, instead of t2 we are plugging 0. So this thing right here is equal to gamma over 2 little gamma, t minus t is 0, minus 2 gamma times 0 is 0, e to the 0 is 1, minus e to the minus 2 gamma, t minus 0 is just t, and we've done calculating the expression for I. So I, we started by calculating I, and we saw that I is equal to this expression right here. So this thing right here is I, and now we can complete the calculation for the second moment. So let's copy this thing right here, and let's put it. Let's see, we said that we've started with saying that we want to calculate the second moment. As we saw, let's put it right here, the second moment was equal, we said that it is equal to this thing right here, and we've just calculated I. Oh, let's look messy. Let's do it like this. Okay. Plus this I term right here. So this is equal to v naught squared e to the minus 2 gamma t plus 1 over m squared, and now times I, and we just found out that I is this thing right here, so times gamma divided by 2 little gamma 1 minus e to the minus 2 gamma t. Let's rewrite it just a little bit nicer. So we have v naught squared e to the minus 2 gamma t plus gamma over 2 gamma m squared 1 minus e to the minus 2 gamma t. And just one quick note, sometimes you can find it in some texts or books written like so. Let's see, we can also this is one way to write it, and another way to write it is, let's do it in green. This is also v naught squared e to the minus 2 gamma t plus, let's see, let's open the brackets here. So we have gamma over 2 gamma m squared minus gamma over 2 gamma m squared e to the minus 2 gamma t. And now we can take this thing right here, so we can write it as v naught squared minus gamma over 2 gamma m squared, these two expressions times e to the minus 2 gamma t plus this expression right here plus gamma 2 little gamma m squared. So these are the two expressions for the second moment. So we can write it, the second moment, we can write it, one way to write it is like so, and the other way to write it is like so. Let's just make it a little bit more nicer. So we said that the second moment of the velocity, the first way to write it is v naught squared e to the minus 2 gamma t plus gamma over 2 m squared gamma 1 minus e to the minus 2 gamma t. This is the first way to write it, and the second way to write it is v, the second moment is equal to, we can put it in brackets, v naught squared minus gamma over 2m squared gamma times e to the minus 2 gamma t plus gamma over 2m squared gamma. So this is these are the two expressions that you can find in some textbooks. They are equivalent, they are saying the same thing. So let's just make a small recap, and let's see. We started by talking about the Langevin stochastic differential equation, where we found the solution. The solution was without the square, and we saw that the expectation for the velocity is given by this, and we wanted to calculate the var, the variance for this process, and for now we've calculated the second moment. We saw that the second moment is equivalent to, we can write it like 1 or we can write it like 2, it doesn't matter. And in the next video we are going to complete this analysis by see what the variance for the velocity time t, what it yields. So this is for now. I'm Alon Sela. Thank you for joining me. I'll hope to see you next time. Bye bye.